Good news, I finally got a new remote. So now I can walk around and do my Ellen impression. But see, really what it lets me do is come up here and say, and look at like people's shirts. Hit me with your best Zot. Oh my God. Do you guys even know who Pat Benatar is? Okay. Because I know you weren't born when that song came out. Okay, I really won't do my best Ellen impression too much. Mainly because I can't walk and talk at the same time. So last time we kind of finished up where we were just going to start going through how to name coordination complexes. And we were going to do examples because, as always, this is the best way to really cement in your mind the kind of 8 rules or whatever that we had on the previous slides and on how to name complexes. So again, we already saw this one. Titanium with 4 dimethyl azonido ligands around it. So this is titanium in its terminal oxidation state, plus 4, which is the most common oxidation state for titanium. And so if we're going to write out the formula, we know that we put the metal first, and then in parentheses we're going to put the dimethyl azonido ligands because, you know, the parentheses tell us that these atoms are grouped together. For the name, we can use 2 different methods. We can either use the Ewing-Bassett system to indicate the overall charge on the titanium complex. So tetrakis dimethyl azonido titanium, the metal comes last in this case. And then we put a space, and in parentheses we put the regular numeral 0 to indicate that the overall charge on the complex is 0. Now again, if you use this Ewing-Bassett method, it's always going to be correct. And you can always back out the metal oxidation state if you recognize that these dimethyl azonido ligands are all 1-, right? This nitrogen has a lone pair on it. And then both of these electrons in the titanium nitrogen single bond would get assigned to the nitrogen when we do oxidation states. So if each one of these ligands is a monoanion, the titanium must have a formal oxidation state of +4. We see that in the second entry, tetrakis dimethyl azonido titanium, parentheses, Roman numeral 4, close parentheses. That's the old stock system, which honestly most inorganic chemists will use this system, though you can get into trouble in some very specialized cases of trying to assign the oxidation state. Again, commonly you're going to see inorganic chemists refer to these as dimethyl amido ligands, but for reasons we discussed last time, that is really not correct and leads to a high degree of confusion, especially when you're talking to organic chemists. Last thing I'll point out with this, you will very rarely see this parentheses 0 in the Ewing-Bassett system. If you don't see a charge, it's assumed that it's 0, okay? We talked about that. Okay, another example. This one's pretty straightforward. We have cobalt with 6 ammonia ligands around it. The overall charge on the complex is 3+. So it's obviously a cation, which means cobalt retains its normal name. And so hexamine, cobalt, again, here we have the Ewing-Bassett, and you can see that the 3+ is written in regular numerals, in parentheses, always with a space after the name of the complex ion. Alternatively, in the stock system, hexamine, cobalt, with the Roman numeral 3 in parentheses and no space. Again, in this case, we have the oxidation state given. Coincidentally for this complex, the oxidation state of the metal is also the overall charge on the trication. And of course, that should make sense to you. If you have a metal oxidation state that's +3 and 6 neutral ligands, then the overall complex charge has to be +3. Our old friend, oh, yeah.
So it says hexamine, is it like vocab where you're supposed to cut one of those off, or do
What do you mean?
I would naturally want to say hexamine rather than hexamine. There's two A's.
Uh-huh. So I'm not sure. You should, if you're going to pronounce it correctly, you're going to use both A's.
Okay.
So hexamine, yeah. Okay, so cisplatin. We have to indicate the orientation or the relative location of the two chlorines. I guess you could argue that you're giving the relative orientation of the two amine ligands, but you only have to do one. In the formula, we list the metal first, followed by the first ligand alphabetically. Amine comes before chloro, and so in the formula, metal first, and then the ligands alphabetically. In the name, we give cis with the hyphen, diamine, dichloro, platinum. So again, in the Ewing-Bassett system, we would normally just drop that parentheses 0 at the end because that's implied. If we use the stock system, then we have to include the metal oxidation state right after the word platinum. Now things get more complicated. So here we have one of our double ions. So a square planar platinum with 4 ammonia ligands and a square planar platinum with 4 chloro ligands. We're going to learn as we go on in the next couple of weeks that anytime you see platinum in a square planar environment like this, you will automatically know that it's in the +2 oxidation state. Okay, so that tells us that this is a +2 cation because the 4 ammonia ligands are neutral. And this must be a 2- dianion because you have 4 negatively charged chlorides. And if the platinum is +2, the residual charge is -2. So when we write the formula, cation comes first, anion second, both appear in brackets. You don't want to lose those brackets because then you lose information about the molecularity of the anion and cation. When we name, again, cation first, tetraamine platinum, followed by the anion tetrachloroplatinate. Okay? Because it's an anion, we give that 8 suffix to remind us that it's negatively charged. Now, because we're naming the entire cation and anion species, for the Ewing-Bassett system, you'll notice that we don't include any charges because they're already balancing each other out. And you will not see the Ewing-Bassett system. You know, you might speculate, oh, I should just put tetraamine, platinum, space, parentheses, 2+, close parentheses, space, tetrachloroplatinate, space, open parentheses, 2-, close parentheses. You will never see that, okay? But what you will see is the stock system where you see we have the Roman numeral 2 to remind us that the platinum center in the cation is +2, and the Roman numeral 2 in the anion after platinate to remind us that the platinum in the anion is also in the +2 oxidation state. Okay, let's get more complicated. It's really not more complicated. Whenever you see platinum in an octahedral coordination environment, we'll learn why in the next few weeks, but you will always know that that is platinum in the +4 oxidation state. Again, we need a configuration label. In this case, we use trans to tell us that the 2 aqua ligands are trans to one another. With the 4 chloro ligands that remain, there's only one way to put them into the octahedral complex. And so the formula is trans platinum, 2 waters, and 4 chloro ligands. And we name this trans diaqua tetrachloroplatinum. If you want to use the stock system, we just put the Roman numeral 4 at the end. Copper complex. By now you're already becoming pros. The copper is, of course, the cation, so it's going to be named first, followed by the tetrafluoroborate anion. So in both the formula and in the name, the copper complex comes first. Here's an example, and I'll tell you that it sometimes will seem very arbitrary to you, but you'll notice we're using the complex numerical prefix. So in this case, it's tetrakis acetonitrile copper tetrafluoroborate, not tetra-acetonitrile. You might, it actually would have been logical for, you use the complex prefix to avoid things like hexaamine, but it's not how it works. And I can't really tell you why acetonitrile is considered to be a complex ligand, whereas amine is not. Just one of these things, that's the way things have developed, and we do just have to remember them. All right, pretty cool complex here. A dihydride of rhodium. So it turns out that this is an intermediate species for a hydrogenation catalyst. So if you just if you eliminate H2 from this molecule, you have 3 phosphine ligands and a chloride, that's known as Wilkinson's catalyst, probably the first molecular hydrogenation catalyst discovered. But if we're going to name it, everybody will know it as Wilkinson's catalyst or Wilkinson compound, but we need to know the correct way to name it. So the formula, cis, fac. Okay, so the cis refers to the orientation of the 2 hydride ligands. Fac gives the orientation of the 3 phosphine ligands. In this case, you need both to define the geometry. Right? Because the other alternative, well, you could of course have trans hydrogens, or you could have the meridional arrangement of phosphine ligands. And you can tell I'm being incorrect by calling them phosphine ligands, because according to IUPAC, the correct name is cis-fac chlorodihydrido tris triphenylphosphane rhodium. And again, that's just to eliminate confusion about phosphine, which is pH 3. Okay, who wants to do this one? Yeah, it got a little bit harder there. So even the formula is a mess, right? Becomes a little bit challenging. And you'll notice we start kind of breaking down the rules, because we've always said that in the formula we should give the metal first, followed by the ligands in alphabetical order. But when you have a dimer like this, a more complicated molecule, it sometimes is helpful to break some of the rules. So you'll notice that we have in the brackets 4 amine ligands followed by the cobalt, followed by the mu2 azonido and the mu2 hydroxyl, and then cobalt and 4 more amines. So we can write the formula in a way that gives some indication of the overall structure of the dimer, right? You have a cobalt with 4 amines on the left, a cobalt with 4 amines on the right, and those 2 cobalt centers are bridged by a hydroxide and an azonido ligand. And so naming this becomes also a challenge. The mu2 azonido, mu2 hydroxo, bis tetraamine, cobalt 4+. Here the 4+ is the overall charge on this dimer, okay? So that's the Ewing-Bassett system. If we were to use the stock system, basically the name stays the same except at the end, inside the brackets for the tetraamine cobalt, by the way, there should be, oh yeah, bis, tetramine, cobalt. So inside the brackets, we have to include that Roman numeral 3 to tell us that both cobalt metals are in the +3 oxidation state. Now, an important point, it doesn't really matter if you use the Stock system or the Ewing-Bassett system, as long as you use them correctly. You should be able to go back and forth. So if you use the Ewing-Bassett system, you should be able to use this knowledge that you have a 4+ charge on the whole complex to back out the charge on each cobalt center. Similarly, if you have the oxidation state of the metal ion, you should be able to use your knowledge of the ligand, of each ligand, and what its charge is to figure out what the overall charge on the complex is. So again, it's just a matter of using each model correctly and not mixing them, okay, so that people are clear on what you're talking about. Okay. So far, we've been talking exclusively about monodentate ligands. Okay, I guess you could say that we've muddied the waters a little bit with bridging ligands, and you can question whether they're monodentate or not. But there are a whole host of multidentate or chelating ligands that inorganic chemists use all the time. So a monodentate ligand, right? Monodentate, one set of teeth, basically, is what this means. Binds to the metal in one place. So phosphane ligands are monodentate. Pyridine is a monodentate ligand. We can very easily consider what a bidentate ligand is going to look like. Well, ethylene diamine, right? Basically, we take two amines and we strap it together with an ethylene linker. In inorganic chemistry, you will often see this ligand abbreviated as just En. Similarly, with pyridine, you will often see it abbreviated Py. It's just more convenient to write Py than it is to write C5H5N. Very popular ligand in inorganic chemistry and coordination chemistry is the 2,2' bipyridine. Nobody wants to write out 2,2' bipyridine, so we just write BIPY, and everybody knows what you mean if you write BIPY, BPY. Or sometimes you'll see it BIPY. It's always the 2,2' isomer because you can take and put a metal. I thought there was supposed to be a metal pop up there. Okay, so at some point a metal is going to pop up there, and then you'll believe me. So we can, it doesn't take a rocket scientist to figure out how we're going to extend this concept to tridentate donors. We'll just string together 3 amines with ethylene linkers, for example. We could put together 3 pyridyl groups to make the terpyridine. Again, if you see terpy written, it always means this isomer, because again, it allows the metal to bind right there. Tetradentate, tri-N, we get really creative. N, di-N, tri-N. Of course, it's a little bit confusing that tri-N is a tetradentate ligand instead of a tridentate, but again, this is what we have. For whatever reason, it's called that because there's 3 ethylene linkers rather than naming it after the fact there's 4 nitrogen donors. Tri-N, of course, is not to be confused with tren, which is this isomer. It's also tetradentate, but this is a really neat ligand because it basically wraps up, and you can think about it as encapsulating half of a metal. So that nitrogen takes up an axial position, and then these 3 come up and wrap up and hold it from 3 positions. Here we go. Another name for multidentate ligands is chelating ring. Chelating. A chelating ring is formed when a metal binds to a chelating ligand. Told you it was coming. Okay, so this is why we always use the 2,2' isomer of bipyridine, because you can see that you bind it to a transition metal, what do you form? A 5-membered ring. Okay, just like for organic chemistry, in inorganic chemistry, 5-membered rings are highly favored and very stable. 5-membered rings and 6-membered rings are the 2 best ring sizes for binding a ligand to a metal. When you start to get 7-membered rings and so on and so forth, it becomes significantly less favorable. Okay, so we've got naming down. We get this idea of multidentate ligands. Let's talk about isomers. And so there's a whole host of isomers possible in transition metal complexes and coordination complexes in general. And what this really comes down to is the fact that metals are cool because they can form more than 4 bonds. And so when you can form more than 4 bonds, you have more spatial possibilities. And so you can go through this flow chart to just identify the type of isomer that you have. So if you have 2 or more identical or molecules with identical formulations, then you have to ask yourself, are the bonds the same between the atoms? Okay? Yes, they are. Then you have configurational isomers, which in Chem 51 we called stereoisomers. And of course, we know that we can go through and compare the mirror images. And if the mirror images are identical, you have diastereomers. Not identical, you have enantiomers. If you have a different arrangement of bonds, then you have constitutional or structural isomers. And in inorganic chemistry, we have these 4 types. Okay, we've already seen ionization isomers. We'll talk now about hydration isomers, coordination isomers, and of course, linkage isomers are kind of pretty neat in their own right. So let's go through these one at a time. Constitutional isomers. Okay, here's an example from organic chemistry. Right, all 3 of these dichlorobenzenes have the exact same formula, but we know that we have different isomers because we have ortho, meta, and para configurations. So in coordination complexes, there are 4 different types of constitutional isomers. The first is a hydrate or solvent isomer, and that occurs when water or some other solvent can bind within the primary or secondary coordination sphere of a metal ion. So a classic example is the hydrated salts of chromium trichloride. And so one version of chromium trichloride hydrate has 6 water molecules in the primary coordination sphere of the chromium-3 ion. So this is a trication that has 3 chloride counteranions, and it's a beautiful violet color. Now you can take that and rearrange it so that you bring 1 chloride ligand into the primary coordination sphere of the chromium. You're left with 5 aqua ligands, 2 chloride counteranions, and then this water molecule sits in the secondary coordination sphere with the chloride anions. The color of the molecule changes from violet to blue-green. You can put 2 chlorides in the primary coordination sphere of the chromium and carry along 2 aqua ligands in the secondary. Now you get dark green crystals. And you can bring all 3 chlorides into the chromium primary coordination sphere, carry the waters along in the secondary, and now the crystals are yellow-green. Okay? So in all of these cases, the formula of the compound is staying the same. Okay? All we're really doing is changing where the waters are carried, waters and chlorides, chloroligands, are carried along in the crystals. Okay? And so it's in a way parallel to these isomers of dichlorobenzene, but in a way different because we have to deal with both the primary coordination sphere and the secondary coordination sphere. So a second type of coordination or constitutional isomer are ionization isomers, and these are for different anions and cations in solution. And so really, in some ways, they're very closely related to these hydrate isomers. So there's two examples shown here, and you can see we're playing the same game. The complex on the left, you have cobalt, you have 5 amine ligands in the primary coordination sphere and a sulfate. The counterion there's 1 nitrate as a counterion. The complex on your right has the exact same formula, except that now we exchange the sulfate for the nitrate, bring the nitrate into the primary coordination sphere, and kick the sulfate out. Okay, so when you would dissolve these compounds in water, the compound on the left would dissolve so that you have a cation, that's cobalt, 5 amines, a sulfate. It'd be a monocation with a monoanionic nitrate. If you dissolve this compound in the right in water, you would have a dication that's cobalt with 5 ammonias and a nitrate, and a dianion that's the sulfate anion. Okay? Same formula, speciates in a completely different way when you dissolve it in water because of the difference in putting the ligands in the primary coordination sphere versus the secondary coordination sphere. So coordination isomers are something that we've seen, and this is our platinum example. Okay? We can have cisplatin. We can take a chloride off of one platinum, transfer it to another, so we have a monocationic platinum and a monoanionic platinum, or we could have a dicationic platinum with 4 ammonias and a dianionic platinum, platinate, with 4 chlorides. These all have the same, in this case, you might say empirical formula, okay? Because you can, obviously, if you were to write out the correct formulas for either of these, you would end up using 2 platinums to indicate that, to give some indication of the ionization and the fact that it's a salt. Perhaps the most interesting, at least to me, of the constitutional isomers are the linkage isomers. And this comes about because certain ligands can bind in 2 different ways. Okay? And so, in this case, we have a palladium with 2 thiocyanate ligands. If we take this complex, where the thiocyanate is bound through sulfur to the palladium, and we put it into a low dielectric solvent, something like hexanes, turns out that those thiocyanates flip over and bind to the metal through the nitrogen. So they bind as isothiocyanate type ligands. If you take that same compound, dissolve it in a high dielectric solvent like acetonitrile, they flip back. So the sulfur binds to the palladium and the nitrogen sticks out towards the solution. So depending on the dielectric constant, you end up with these ligands kind of tumbling even though they never leave the metal coordination sphere. Yeah?
Would this be classified as a diastemer or enantiomer?
Because the molecule has a mirror plane. Right? So remember, that should be your go-to way to decide if you have an enantiomeric complex. Does the molecule have a mirror plane? The fact that this is a planar molecule means that it has a mirror plane. Any other questions? Yeah?
What exactly is the dielectric solvent, or what
has to do with the polarity of the solvent, how well it also conducts charge. And so there's a couple of different things that go into it.
Does this have anything to do with the hard soft acid base?
Really good question. So did everybody hear? Her question was, does this have anything to do with hard, soft, acid-base concepts? Really, really good question. So if you look at that thiocyanate ligand, right, when it's bound to palladium through the sulfur, we know that sulfur is a really soft ligand. Palladium is a fairly soft metal. Nitrogen, on the other hand, is a hard donor. Okay, so it has everything to do with hard, soft, acid, base. And what this is really telling you is that palladium is right on that border between whether it wants a soft ligand or a hard ligand, and you can change its preference by changing the properties of the solvent around it. Okay? And what that comes down to is we have to remember that when we dissolve a molecule in a solvent, there's all kinds of interactions between the solvent and the portions of the molecule that are sticking out. Okay? And so in a low dielectric solvent, typically that's not going to form strong interactions with the complex. Okay? But a high dielectric solvent will do things like hydrogen bond. Okay? So water is a very high dielectric solvent, or an alcohol is a high dielectric solvent. Well, if you think about one of those hydrogen bonding solvents, what would it prefer to have sticking out? A nitrogen atom, right? And then, so that induces the palladium to accept the softer donor. Really, really good question, though. Here's another example. Octahedral cobalt complex with this NO2 ligand. The ground state, the lowest energy conformation is for it to be oxygen bound to the cobalt, but this complex will absorb a photon of light, and when it absorbs a photon of light, it goes to an excited state, and that NO2 tumbles and becomes a nitrogen bound ligand to the cobalt center. Basically what happens is you get trapped in a local energy minimum. The compound is stable, but if you heat it up, you can give it enough thermal energy and drive it back to the ground state, which is the oxygen-bound version of the ligand. So basically this is a photoisomerization of the NO2 ligand. Okay. Stereoisomers. As much fun as stereochemistry was for organic compounds, it's even more fun for inorganic compounds. So we know the ground rules here, right? Same connectivity, basically a different geometrical representation in space because of a lack of mirror planes, at least for enantiomers. And so you can have cis-trans isomers. These are configurational isomers. And as we've seen, it's when you have pairs of ligands and they can appear either next to each other or across from each other. Cis and trans can only occur really in square planar complexes and octahedral complexes. Some people will say it can happen in trigonal bipyramidal, but we'll see later on why that isn't really of concern. So there's an example. There's our favorite cancer drug example, cisplatin versus transplatin. Again, in an octahedral complex, you can have the two chlorides cis to one another, or you can have them trans to one another. We've already seen FAC and MER isomers. Same idea, except the ligands appear in pairs or in threes instead of twos. And so the FAC isomer, you'll have three ligands that basically define a trigonal face of the octahedron. For the MER isomer, you'll have three ligands that form a meridional belt around the coordination complex. So again, two isomers of the same chromium compound, depending on whether the ligands are arranged in a facial or meridional way. Typically, you cannot convert between these two. Okay? If I end up flipping through slides too fast and you can't write down the structures, because I know they're missing, just feel free to tell me to slow down. Or I guess ask me to slow down. You can be polite. Okay, so we all love symmetry. Talked about using mirror planes to define whether a molecule is chiral. So basically, if you have mirror planes, it ain't chiral. Okay, another way to say this is if a molecule has only proper rotations, then it is chiral. Okay, so anytime you see improper rotations, that throws the chirality thing off. And so we can look at a molecule, no surprise, if you take an octahedral molecule and you throw lots of different ligands on it, you can get a chirality. If you put the ligands in the correct arrangement, you won't. So here we have iron, we have two ammonias, two waters, and two chlorides. But this is the all-trans isomer, so we only give trans because by definition the third pair has to be trans. It falls into the D2H point group. It's not a chiral point group, not a chiral molecule. We can take the same three pairs of ligands around iron. Now we have the trans cis. Okay, so again, in this case, it's the transamine, cis aqua, and by definition, the chlorides must be cis. Okay, because those are the only two spots left. It's a C2V molecule. It's not chiral. If we go to the cis-cis isomer, the first cis tells us that the amines are cis. The second cis tells us that the aqua ligands are next to each other related by 90 degrees. And by default, the chlorides have to be related by 90 degrees in a cis conformation. That molecule is C1 symmetric. No mirror planes, chiral. Okay, so we have two isomers with essentially the same connectivity, right? Each ligand is bonded to iron. That doesn't change across the series of three complexes. Just their relative orientation in space when they form their bond to the iron is the only thing changing. So we get two non-chiral versions and one chiral version. Here's where things get really crazy. These chelating ligands we use also can bring about chirality in a compound. Okay, so here is our tri-N ligand. So our tetradentate, four amines bridged by three ethylene linkers. And so if you think about how this wraps around in space, you should be able to convince yourself that it really can only bind to a transition metal in one way, and that's to take up two axial positions and two equatorial positions. You can sometimes get it to take up three equatorial positions and an axial, but this is the more common configuration. And it turns out that this molecule is chiral. It has a C2 axis that bisects this carbon-carbon bond and then goes through the chromium and bisects the chlorine-chromium-chlorine angle. So that's the C2 axis. But because of the way this ligand wraps around, there are no mirror planes. And so if we represent this molecule just by these loops, again, very important that you use wedges and dashes so that you can keep it straight in your mind whether things are coming out of the screen at you or going back into the plane of the board. But if we use just these curly cues to remind ourselves the way it wraps around, we can do the old organic trick, draw a mirror plane and reflect the molecule through. Okay, so there's the reflected version of the molecule. And now if we try and take this orientation or this reflection and rotate it so that to see if it overlaps on the original picture. Okay, I was pretty careful to make sure that I kept the loops connecting in the right way. What we see now is that this amine on top, the loop connects it to the amine in front, versus the original orientation, the amine on top was connected to the amine in the back. Okay, and so because of the way this ligand wraps around, it has a handedness to it. Okay? And when we reflect, we get the opposite hand, which tells us that this must be a chiral molecule. But again, if you assign the point group correctly, you get C2, you know that it cannot be it has to be a chiral molecule. More complicated examples. If we take 3 ethylene diamine ligands and put them on cobalt, each one of these ligands has, again, a way that it wraps around the metal center. Okay? And so we have 2 different isomers. In this case, the dotted line is meant to be a mirror plane that we reflect to show the 2 isomers of this tris ethylene diamine cobalt trication. And so we're looking down a trigonal face. So we can define that trigonal face of the octahedron by the amine on top and these 2 amines that are coming out of the board at you. And you can kind of convert this over into a Newman type projection to see the chirality. And so what actually happens, again, these ethylene diamines wrap, and when you're looking down this 3-fold rotation axis, you'll notice that it forms a screw. Okay? The screw on your right is a proper screw, right? If you were to pull out a screwdriver and try and screw this in, you would have to, righty-tighty to drive it into the plane of the board. The version on the left is a left-handed screw. That would screw you up. Lefty-loosey, righty-tighty. But this one, you'd have to turn to the left to get it to screw into the board. Okay? Again, this is a C3 symmetric molecule. There's no mirror planes, and so these 2 are enantiomers. This is a special example of an enantiomer that you can only get in inorganic chemistry, where you can access octahedral complexes. Left-handed screw, right-handed screw. And so the left-handed screw is called the lambda isomer. The right-handed screw is the delta isomer. Now it turns out you can go through and assign the handedness to each individual ligand as well. Your textbook talks about that. And each individual ligand can have a left-handed twist or a right-handed twist, and you can get mixtures. And those are typically given lower hand lambda or lowercase delta to indicate the twist of individual ligands. But for our purposes, we'll be interested mostly in the overall handedness of the entire complex. Okay, so ring twist. It turns out rings can also give rise to chirality, but only if the chelating ligand is non-planar. So if we look at BIPI, we said that BIPI binds to a transition metal in this chelating fashion to form a 5-membered ring. If we take this and we rotate it down so that we're kind of looking down the plane defined by the metal atom and the 2 nitrogen ligands, what we would see is that it's completely planar, right? So that individual metal chelate ring unit has a mirror plane. Okay, so it can't be chiral. On the other hand, if we look again at ethylene diamine, okay, we know that when this backbone is saturated, it's a non-planar type species. And so if we might draw the 5-membered ring like this, but if we rotate and look down that same plane defined by the metal atom and the 2 nitrogens, what we would see is that there's a kink because of the sp3 hybridization of the carbons in the ethylene linker. Okay? And so you can get 2 isomers. You can get the lambda isomer. Again, this is the left-handed screw. And you could get the delta isomer, the right-hand screw, of that individual ethylene linker, that individual chelate ring. Now, the number of cases where this is important is small. Why? Because the barrier to a ring flip, to this ethylene linker flopping back and forth, is only 1 to 2 kcals under most conditions. Okay, so basically what happens is at room temperature, the linker is doing this, flipping back and forth between the delta and lambda isomer. Okay? However, in the solid state, you can sometimes see the difference of the isomers. Okay. We'll end with this slide. On Monday, we're going to go through quickly the common coordination geometries for coordination complexes. Again, a lot of this will be a review from freshman chemistry, okay, where you were mostly taught it within the context of VSEPR. But for our purposes, it's important to think about the factors that affect coordination geometries. The first thing to always remember is that more bonds generally is more stable. Okay? Metals are Lewis acids, ligands are Lewis bases, and so the more times you bring a Lewis base up to a Lewis acid, the more you stabilize it. We also know that if you have a Lewis base, a lone pair of electrons, and you bring it up to a Lewis acid, an empty orbital, it always lowers the energy of that electron pair. Okay? So anytime you lower the energy of an electron pair, it generally stabilizes the molecule. Or that's a stabilizing effect. D orbital occupancy. We're going to have lots of fun with d orbital occupancy in the next couple of weeks. Okay, the coordination geometry adjusts to accommodate non-bonding electron pairs in the d orbital manifold. And that's one of the things that gives rise to the interesting structures that transition metal complexes can have. Now, the counter to point 1, more bonds giving more stable structures, the counter is sterics. Okay? Obviously, you can't just keep bringing in Lewis bases, more and more Lewis bases to a metal. At some point, things get crowded. Okay? Sterics will eventually prevent you from bringing another Lewis base into your Lewis acidic metal center. The bigger the Lewis base is, the quicker sterics will become a problem. Okay? Crystal packing effects and solvation effects. So we've already seen some solvation effects. Okay? We can switch a ligand from being an S donor to an N donor with solvent effects, playing with hard, soft, acid, base. Crystal packing ends up being pretty important for inorganic chemistry, if only because it's a science that's so dominated by solid state structures. Okay? NMR is not nearly as useful a tool in coordination chemistry as it is in organic chemistry. only because we often are dealing with paramagnetic compounds. Last thing, VSEPR is great for p-blocks. For transition metals, not so much. And that mainly comes down to point number 2 here. The d orbital occupancy will often screw with the predicted VSEPR geometry because VSEPR is effectively a steric argument, and the electronic factors from d orbital occupancy can overrule sterics in some cases. So with that, have a great weekend, and I will see you bright and early Monday morning.